Hello everyone, welcome back to Chemical Engineering and Aspen Channel. As you know, these days we are focusing on the module of Chemical Reaction Engineering, and so far we have presented 37 videos for our valuable viewers. But today we are now bringing the lecture number 38 for our valuable viewers, in which we will be talking about the method of half-life. So far in this chapter number 7, which is related to collection and analysis of rate data, we have studied three methods. Number one was the integral method, method of excess, and in last lecture we have studied the method of initial rate, and now today we will be studying the method of half-life. The half-life of a reaction T1 by 2 is defined as the time it takes for the concentration of the reactant to fall to half of its initial value. We definitely know the value or the definition of half-life. So the same definition will apply once we talk about the collection and analysis of rate data. By determining the half-life of a reaction as a function of initial concentration, we can determine the reaction order and the specific reaction rate. So we can determine the different rate parameters based on this method as well. Earlier we have studied the previous three methods like the method of excess, integral, and the method of initial rate to determine these parameters, and method of half-life can also help us in determining these parameters. But now we will proceed how we can mathematically solve it. So let's assume that the species A converts to products. So the mole balance, obviously we are talking about the batch reactor, because for collection and analysis of rate data, we use the batch reactor. So the mole balance or the design equation can be written as minus RA is equal to minus dCA over dt is equal to kCA raised to power alpha. Obviously the alpha is an unknown parameter and we have to find its value. The alpha is obviously the reaction order in the system. Then if we integrate it after rearranging that, we take C here raised to power alpha here and dt here, and then applying the integration limits for at time t is equal to 0, the concentration is C naught. At time t is equal to t, the concentration is C of A. So accordingly, we come up with this solution that t is equal to 1 over k bracket alpha minus 1, then 1 over C raised to power alpha minus 1 minus 1 over C naught raised to power alpha minus 1, or we can say it as, if we take out Ca naught alpha minus 1 out of this, then we get 1 over k Ca naught raised to power alpha minus 1 into alpha minus 1 bracket Ca naught over Ca whole raised to power alpha minus 1 minus 1. So this is the equation for time. But now we have to convert this equation into half-life equation. So what we can do, that the half-life is defined as the time which is required for the concentration to drop half of its initial value, that is that T is equal to T1 by 2 and Ca is equal to 1 by 2 of Ca naught. Obviously the concentration is halved with the time. So accordingly, writing in terms of half-life the previous equation, that will become as T 1 by 2 is equal to 2 raised to power alpha minus 1 minus 1 over k into alpha minus 1 over 1 over C naught alpha minus 1. Once you will be solving it on the paper, you will be able to solve the steps, 1 to 2 steps, and you will be able to come to this solution. For value of n number of times, we can write T1 by n is equal here, and here is replaced by n. The rest of the equation will remain the same. That T1 by n is equal to n raised to power alpha minus 1 minus 1 over k bracket alpha minus 1 into 1 over C naught alpha minus 1. Taking natural log of that equation, we get natural log of T1 by 2 is equal to natural log of 2 alpha minus 1 minus 1 over k into alpha minus 1 plus 1 minus alpha natural log of Ca naught. And if we draw the plot using the straight line method, that it is y is equal to mx plus c, so the plot will be generated between natural log of T1 by 2, which will be at y-axis, natural log of Ca naught, which will be at x-axis. The slope of the line will be 1 minus alpha, while the intercept will be this parameter. So let's see that once we have drawn a plot, we got the slope, and that is equal to 1 minus alpha. So let's assume that the value of slope is 1. So accordingly, the alpha will be 2, because 1 is equal to 1 minus alpha. So alpha is come out to be 2 in the system. And we can write the rate law as minus Ra is equal to Kca square. So this is the description of how to use half-life method to determine the reaction order. In the same way, or using the same parameters, we can determine the value of reaction rate constant as well. I hope you have understood all the aspects related to the method of half-life. If you have any queries, feedback, suggestion, please provide it in the comment box and I would be happy to answer. So that's it from today's lecture. Thank you so much. Please do watch, like, share the video and subscribe to the channel. Also click on the bell icon to get all updates related to this channel. Till then, it's goodbye. Stay tuned for more exciting videos on this channel.